Okay, class, we're about to start section 3.1, using graphs and tables to solve systems. It says here, review. We know that a linear equation in two variables has infinitely many solutions. Example, y is equal to 2x minus 1. A few solutions would be 0, -1, 1, 1, 2, 3, and also 3, 5. Now we know there are more solutions than this, but this is just a few solutions to this linear equation. It says here, what are two ways we can use to visualize multiple solutions? We could do that by tables and graphs. Why are these methods unable to show all solutions? Because they would have to go on forever. Okay. Now we scroll down here. It says system of equations. A set of two or more equations with the same unknown variables. In this chapter, we will look at two linear equations and two variables. Solutions to a system of equations. Any point that satisfies all the equations in a system. That is, it makes all the equations true. For example, we have these two equations here. We need to know what point or points will work in both of these equations. And if it's one point, our answer would be the one point that work in both of these equations. If it's multiple points, then it will be multiple answers. And then if it's no point, then we will have an answer for that as well. So, now on your page, the next part will be this here. It says A, explain how can we tell that both equations are linear? How many variables do they contain? So the first thing we would do is this here. We would fill out this graph here. As a matter of fact, okay class, there was a little slight error here on the page, but I corrected it. We go back to example 1. Consider the system of equations. We have y equals 2x minus 1 and y is equal to -x plus 5. Okay, now we have A. It says, explain how can we tell that both equations are linear? How many variables do they contain? So the first thing is this here. We can tell that both of these equations are linear because both only has at most two variables. And both variables are taken only to the first power. That's one way we can tell. And also another thing too, if we graph these equations, we know that they will form a straight line. Okay, it says how many variables do they contain? If you notice, they only contain two variables. So they have two variables. Also, going back to the first question here about explaining how we can tell that both equations are linear, because these are set up in slope-intercept form, you know, y equals mx plus b. That's also a way of telling that it's linear because this is always linear when it's in slope-intercept form. Okay, now we look at B. It says fill in the tables at right for each equation. So what I did here, I took the liberty of filling in these tables here. Okay, now it says C. What point do the linear equations have in common? Okay, now, if you look here, if we look down here when x is 2, both of these y values are 3. So the point they have in common is 2, 3. This point is called, it should be an, A-N, intersection. It says here D. Does the system have any other solutions? And as you can see by the lines drawn here, that they do not have any other solution. So your answer here would be no. And it only intersects once. Okay, so let's go back over this. We have our two equations here. We actually would graph those two equations. We noticed that we had an intersection point here, which is the only point that both of these equations have in common. So that would be the solution of this system of equations. And this is the only solution that they have, and that's where they intersect. Okay, now we go here to example 2. It says solve the following systems by graphing. Now what I did for the sake of time, I had already graphed these system of equations. But before we get to the graph, what I want to do is go through and show you what we need to change this equation to before we even get to graphing. So the first thing is this here. We want to change both of these equations so they would be in slope-intercept form, which means y being by itself. So let's take this top equation. We have 3x plus 2y equals 16. We'll subtract 3x on both sides. And we will have 2y is equal to negative 3x plus 16. We'll divide each side by 2, each individual term. And we will have y is equal to a negative 3/2 x plus 8. Okay, now this is one equation. Now our next equation, we would take this one here. Now the first thing we need to do is get rid of these denominators. So we'll multiply everything by the common denominator, which is 6, which is 6 over 1. So 6 and 6, they will simplify out, and this would just leave you x. 2 goes into 6 3 times. 3 times a negative 1y will give you a minus 3y. And then 2 goes into 6 3 times. 3 times 3 is 9. Okay, now we want to get y by itself. So we will subtract x on both sides. We had negative 3y is equal to negative x plus 9. Divide each individual term by negative 3. And we will have y is equal to 1/3 x minus 3. Now, what we would do is this here. This line here goes with this first equation here. I plotted a point at 0, 8. I plotted another point at 4, positive 2. Plotted another point at 6, negative 1. Plotted one more at 8, and this will be negative 4. Now you could go in and put in those values, and you would get these values for this graph. Now for the second line here, I substitute in values negative 3 for x, 0 for x, 3 for x, and also 9 for x. And it gave me this line here. Now their point of intersection is here. It's at 6, negative 1. So the answer here would be 6, negative 1. Now, because it tells us to solve this system of equations, it's only one answer, so it's 6, negative 1. And then we also know that this is conditional. And it's also consistent. And this here is your total final answer. Now, we scroll down here to B. Now with B here, we already have one equation set up in slope-intercept form. So we want to do the other equation. So we add 2x on both sides. We add 3y is equal to 2x. Divide each side by 3. And y is equal to 2/3 x. So now, if you notice here, both of these equations have the same slope. Now, this line here is the one derived from this first equation here. I use 0 for x, I use 3 for x, I use 6 for x, and also 9 for x. I picked the convenient point. Now remember, we studied that back in, I believe it was chapter 1 about convenience points, because it's based upon the denominator here. And then this line here is based off of this equation here. I use points -3, 0, 3, 6, and also, well, I didn't put in 9, but you could also put in 9 as well. Now, if you look here, these lines will never intersect. So this would be considered to be, a lot of times it would be no solution. You could write no solution. Or sometimes, depending on the book, it would just say parallel lines as well. So either one of these answers would be acceptable. No solution or parallel lines. It says here, this type of system is called inconsistent. Okay, now we go to C here. Now, if you notice, both of these equations are not set up in slope-intercept form. So that is the first thing that we want to do. Now, we have to do it actually for both equations. So what I'm going to do, I'm going to write one equation here, and then another equation on the other side. This is just to give room. So we will subtract 6x on both sides. This will give a -10y is equal to -6x plus 30. Divide each individual term by -10. And y is equal to, we know a negative divided by a negative is positive. We could divide the numerator and denominator by 2. So that would be 3/5 x. And a 30 divided by -10 will give us -3. So this first equation has been set up in slope-intercept form. Now the second equation, first thing we'll do is subtract 9x on both sides. We have -15y is equal to -9x plus 45. Divide each individual term by -15. And we will have y is equal to a negative divided by a negative is positive. We could divide 9 and 15 by 3. Now to give us 3/5 x. And a positive 45 divided by a -15 will give us -3. Now if you notice here, both of these equations are exactly the same. So their graphs will be exactly the same. They will be right on top of each other. It'll look like it's just one line. But you notice it's two separate equations, so you know this is two lines. Now, this type of system is called dependent. And also, this is said to be infinitely many solutions. Or sometimes it's stated to be, or all real solutions. So either one of these answers would be acceptable. Now we come to example 3. It says the table below shows the number of births in millions in the U.S. for both Hispanic and non-Hispanic white babies, according to the U.S. Census Bureau. Let B equals HT be the number of Hispanic babies born in the U.S. T years since 2000. Find an equation for H of T. Give 3 decimal places. First of all, we would change this. They said since 2000. So these years here would actually be 3, 4, 5, 6, 7, and 8. And we know that that is our T. Now, one other thing you need to know is this here. We know we will put this in a calculator because we're going to do a linear regression model. So we know this will be our L1, this will be L2, and this will be L3. Actually, your L1 would be this column here with the 3, 4, 5, 6, and 7. Okay, so now after you put this in a calculator, this is what you would end up with your linear regression. You have B of H of T is equal to 0.030t plus 0.833, because we said